So now we're going to move away from equilibrium and into what's called a redox reaction. And so today we're going to learn about oxidation and reduction and the basics before we get into how to balance these special kinds of reactions. You've already balanced some in a very simple form, but now we're going to move on to the more complicated ones. So first we need to look at oxidation numbers. And oxidation numbers are the apparent charge on an atom. It's very similar to charge, but it's not 100% the same. And so there are some rules that you need to know. And so our rules go, the oxidation number on any uncombined element, basically any element that's just sitting there in a reaction, often it's a metal like silver, or a gas like hydrogen, H2 or Cl2, any uncombined element in its standard state is 0. The oxidation number of a monatomic ion is equal to the charge on the ion. So what that means is that if it's something with a charge like copper +2, then its oxidation number is +2. Or if it's lithium +1, then its oxidation number is +1. If it's chlorine -1, then its oxidation number is -1. The oxidation number of hydrogen in most compounds, there's always some exceptions, but 99% of the time hydrogen is going to be +1. And the same is true for oxygen, except oxygen is going to be -2. The one notable exception with oxygen is peroxide. And then finally, the sum of the oxidation numbers of all the atoms in a particle must be equal to the apparent charge of that particle. So we use the word particle because if it's a compound and it's neutral, then the charges, the oxidation numbers, must equal 0. If it's an ion and it's charged, then the sum of the oxidation numbers must equal that charge. So let's look at determine the oxidation numbers in each of the following reactions. So here's our first reaction. And so what we're going to do is we're going to go through and assign the ones that we know. And there's a lot of hydrogen and oxygen, and so the format that I like to use, it's not any real prescribed format, but I like to write the oxidation number above the element, and then I keep a tally of my total charge below. So I know that hydrogen is +1. One hydrogen is going to be +1, but I have 2 of them. So I know my total charge here for hydrogen is +2. I'm going to do the same thing with oxygen. It's going to be -2, but I know my total charge here is going to be -2 times 4, so -8. And then any other element, we just sort of fill in to finish the gaps, to finish what it needs to be. So this is a compound, and it's neutral. And so I have a +2 and a -8, which means sulfur must be a +6. And I know if we look at sulfur in the periodic table, it's in the -2 group, but it's related to charge. Oxidation numbers are not charge. So by using the ones that we know, we'll piecemeal in and be able to figure out the other elements. In this case, hydrogen is a +1, and that's easy because it's 1. Oxygen is a -2, and that's going to be -2. And now I know my whole compound has to be 0. So in this case, I know that sodium needs to be a +1, because +1 minus 2 and +1 is going to equal 0. And that matches up with its charge, so that's pretty good. Here, I'm going to make oxygen a -2, and so that's a -8. And then when it comes to figuring out which elements here are going to have what charge, they do change from side to side. When it comes to figuring out which one we should use, I tend to use my alkali metals, or my things that are really electronegative. My non-metals are what I leave for last. So I'm going to say sodium is going to stay as a +1. And that really does work out okay because sulfur in this case stays as a +6. And then here, oxygen is a -2, hydrogen is a +1, and so that balances out. So now we've assigned the oxidation numbers are the numbers that are above. These numbers that are below are not required. They're not required for anything. But that's the way I keep track of the problem. So you never have to put the ones down below. You only have to put the ones up above. So let's try another one. Here we're going to start right off the bat. It's an element. It's rule 1. The oxidation number on a free element is 0, so that's going to be 0. If we look, is there any other zeros we see? Sure, silver is going to be 0. So those ones are done. And now we're going to work through. oxygen here is going to be a -2, so I'm going to have a -6. And silver is one of those ones, it's always a +1, plus it's nice to sort of split up my polyatomic, so if I know what charge this is bringing, I'm going to say that this is a +1. And that nitrogen here, in order to balance this all out, is going to be a +5. And nitrogen is that non-metal, so that's why I'm saving it for the end. If I look here, oxygen is a -2, and if I want to keep the whole thing balanced here, I have a -2 times 3, that gives me -6, and I have 2 of them, so my total charge for the oxygens is -12. My copper, I'm going to pretend, if I had to figure out what it was, what charge it was, if it's balanced to these nitrates, nitrates -1, and I have 2 of these here, so I'm going to keep my copper at +2. So I have a +2 and a -12, which means in here I need a +10. Nitrogen isn't going to end up being a +10. What I have to look at is that I have 2 nitrogens that must equal +10, which means each of them must equal +5. And so in a redox reaction, it's a reaction in which electrons are transferred and oxidation number changes. If we go back and look at our first reaction, hydrogen is +1, hydrogen is +1, okay? It didn't change. Sulfur is +6, sulfur is +6, it didn't change. Sodium is +1, sodium is +1, it didn't change. And I think we did oxygen. I think we did oxygen's -2, and it's -2 in all of them. So this is not a redox. Oops, sorry. This is not redox, which stands for reduction and oxidation. Let's look here. Copper is 0, and copper then becomes +2. That's a change in oxidation number. Silver is +1, and then silver becomes 0. That's a change in oxidation number. Nitrogen is +5, that stays the same. Oxygen is -2, that stays the same. So this one, yes, is a redox reaction. So reduction is the gain of electrons by atoms or ions. Oxidation is the loss of electrons from an atom or an ion. There's an easy way for us to remember there's 2 different acronyms. We can either say Leo, the lion, says grr, or Leo goes grr, because we can say that it's loses electrons, that's our symbol for electrons, we're going to use that a lot, oxidized, and then gains electrons, reduced. Or we can say oil rig. Oxidation is loss. Reduction is gain. So whatever one you choose, Leo the lion or oil rig. Your oxidizing agent is the substance that tends to gain electrons. Your reducing agent is the substance that tends to lose electrons. Your oxidizing and reducing agents will always be in your reactants. And these will always refer to in our products. So let's try it out. Here's our reaction. We need to go ahead and assign oxidation numbers. Element by itself, 0. Oxygen, -2, with a total of -6. Hydrogen, +1. And then I need to fill in the middle. I have a +1 and a -6, so nitrogen will be a +5. I come over here. Oxygen is a -2. -2 times 3 is a -6, but I have 2 of them, so it's a -12. I'm going to go with this copper being a +2 because of this nitrate. I'm just going to go in and fill in what it would have been. And then I'm going to save this nonmetal as my sort of wild card. And again, it's +2 and -12, so I need a +10 in here. But again, I have 2, so this is a +5. This is a -2, which automatically puts this nitrogen in as a +2. And oxygen here is a -2. which means this is a +1. And so all of my things balance. Now, let's look and see where my oxidation numbers have changed. Start with looking at copper. Copper goes from 0 to a +2. It's +2, but in order to become positive, it lost electrons. So losing electrons, we're going to refer to this as oxidized. If I look at my nitrogen, nitrogen stays the same here, so nothing's happening here, but nitrogen goes from a +5 to a +2. +5 to +2, it must have gained electrons. Gained electrons, it was reduced. And so the hardest thing to remember is that losing electrons sometimes appears to look like it's becoming more positive. And so because it's +2, you just have to really think about that electrons are negative. To figure out our agent, it's really easy. We just look back and say, well, this is what's oxidized, so this is my reducing agent. And this nitrogen is what's reduced, so this is my oxidizing agent. Okay? Just like we had bases become conjugate acids and acids become conjugate bases, same thing. They sort of become the opposite. Here's our second example. H is +1, so I have a +2 here, which means S must be -2. Br is an element by itself, so it's 0. Sulfur, element by itself, so it's 0. H is +1, which means Br is -1. So let's take a look at this. H is +1 on both sides, no change. S goes from a -2 to a 0. To go from something negative to 0, it must have -2 to 0, it lost electrons. So if it lost electrons, it's oxidized. And Br went from 0 to -1. In order to become negative, it must have gained electrons, so it's reduced. And then we'll just flip-flop and go backwards. This is our reducing agent. This is our oxidizing agent. Last example, and last for today. This is an element, so it's 0, element, 0. And this goes to a -2, and this goes to a +1. And so I look at it. Hydrogen goes from a 0 to a +1. It lost electrons, loses electrons, oxidized. Oxygen went from a 0. So if this hydrogen was oxidized, this is my reducing agent. Oxygen went from a 0 to a -2. It gained electrons. So this compound was oxidized and reduced, and that is okay. They can both be in the same one. This is going to be my oxidizing agent. So unlike acids and bases where they can't be in the same one, oxidizing and reducing agents can be in the same one. So you want to make sure you have a good understanding of this, because then we're going to take this to learn how to balance redox reactions.